ask me, why does quantum mechanics matter, given that it's little tiny stuff? Who cares? There are three possible answers. From a practical point of view, it doesn't make any difference at all. I mean, you still have to go to work and drive your car and do all the rest of it. From a second point of view, it actually infiltrates everything in the world, especially the world of electronics. But I think the important part is the third one, which is essentially a philosophical issue. Why are philosophers so passionate about deconstruction the assumptions of the world? I finally got it. I got it as a result of looking at quantum mechanics and comparing it to classical mechanics. They present two very different ways of thinking about the way that the world works and about what we are. So from a classical perspective, we are machines. And in machines, there's no room for a conscious experience. It doesn't matter if a machine dies, you can kill the machine, you can throw it in a dump, it doesn't matter. If that is the way that the world is, then people will behave in that way. But there's another way of thinking about the world which is suggested, it's pointed to by quantum mechanics, which suggested that the world is not this clockwork thing, but it's more like an organism. It's a highly interconnected organismic thing of some type, which extends through space and time. And that kind of environment, what I think and the way that I behave has a much greater impact, not only on myself, but on the rest of the world, than it would if it was a classical world. So from a very basic point of view having to do with morals and ethics, what I think affects the world. That's, I mean, in a sense, that's really the key for why a worldview change is important.
The universe is very strange. There seem to be two sets of laws that govern the universe. In our everyday classical world, meaning at roughly our size and time scales, things are described by Newton's laws of motion, set down hundreds and hundreds of years ago. And they work very well for billiard balls and cannonballs and gravity. However, when we get down to a small scale, when we get down to, say, the level of atoms, a different set of laws take over. These are the quantum laws, quantum theory, quantum mechanics. And at that level, particles may be in multiple places at the same time. They may behave as waves smeared out spatially and temporally. They may be interconnected over great distances. They may be unified into one quantum state, into one state, governed by one wave function. And the borderline, the threshold, this curtain between the quantum world and the classical world is really mysterious. It's called sometimes the collapse of the wave function, because in the quantum world, everything is in superposition of multiple possibilities, and in the classical world, these multiple possibilities seem to collapse to particular definite choices, so everything is in one particular place.
What is the field that is waving? An ocean of pure potentiality, an ocean of abstract potential existence. We call it the unified field, or superstring field, and that's what we're made out of.
Connectivity among all things is a basic constituent of the fabric of reality. It's very difficult to wrap your mind around that. But Erwin Schrödinger said, he's one of the founders of quantum mechanics, that entanglement, which is this idea of this connectivity, is not just a property of quantum mechanics, it's the property.
And that's what the unified field is. It's pure abstract potential, pure abstract being, pure abstract self-aware consciousness, which rises in waves of vibration to give rise to the particles, the people, everything we see in the vast universe.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now, there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through, the electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Masaru Emoto. Mr. Emoto became terribly interested in the molecular structure of water and what affects it. Now, water is the most receptive of the four elements.
For one sample of water, we drop about 0.5 cc's onto each 50 petri dishes. Then we take those 50 petri dishes and freeze them in a freezer at minus 25 degrees Celsius for about 3 hours. We take those frozen samples into a refrigerator that is set at minus 5 degrees Celsius, where a microscope with a camera is set up. There we take photographs of each of the 50 water drops individually. We first take photographs of water that we did not put any information in. Then, we take the water with information and do the same procedure just described. We take those before and after photographs and compare the differences. When we projected the feeling of love and thanks to water, it made the most beautiful crystal.
This first picture is a picture of water from the Fujiwara Dam. And this picture is the same water after receiving a blessing from a Zen Buddhist monk. Now, in this next series of pictures, Mr. Emoto printed out words, taped them to bottles of distilled water, and left them out overnight. This first photograph is a picture of the pure distilled water, just the essence of itself. These subsequent photographs, as you can see, are each different. This is the chi of love. Now, Mr. Emoto speaks of the thought or intent being the driving force in all of this. The science of how that actually affects the molecules is unknown. And it's really really fascinating when you keep in mind that 90% of our bodies are water.
Makes you wonder, doesn't it? If thoughts can do that to water, imagine what our thoughts can do to us.